Push that rock with Simpson math. Let's talk about limits. So, the direct substitution theorem says that if the function is continuous at this x value, you can just direct substitute in. But the problem here is that the function is not continuous at this x value, so I cannot just substitute in. So what am I going to do? Well, I'm going to look in here, and I'm going to realize that if you go x plus 1 times x plus 1, and then you feel what that is, and then when you're done with that, multiply it by one more time. Sorry about those dogs. You get x cubed plus 3x squared plus 3x plus 1. So I have this right here cubed is that big long polynomial minus that 1. That's going to give me x cubed plus 3x squared plus 3x, because this one and that one go away. Meanwhile, on the bottom I have x squared plus 2x. But wait a minute. They have a common factor of x. So we can factor out an x and get x squared plus 3x plus 3. And we can factor out an x in the bottom and get x plus 2. And those will reduce. And so by our favorite property, OFP, by our favorite property over here, we can replace this function with an equivalent function. And the equivalent function is x squared plus 3x plus 3 over x plus 2. And guess what? This function, that's a 2 right there. Sorry, terrible handwriting. But that's an x plus 2. So this is discontinuous at -2, but continuous at 0. So now we can direct substitute. Put 0 in, all the x's go away, and you're left with 3/2. So the limit of this function is 3/2. Let's try our hand at another one. Okay, well, remember direct substitution. If it's continuous, you can just direct substitute the x value, what the x is approaching for the x value. Well, exponentials are continuous. Exponentials are continuous. When you add two continuous functions, guess what you get? That's right, a continuous function. So I get 1/2 squared plus 1/3 squared. Okay, well, what is that? Well, that's 1/4 plus 1/9. I got to get a common denominator. Oh, well, just they're both going to 36. Okay, so this will be 9 36s, and this will be 4 36s. And so when I add that together, there's a 9, and that 4 makes 13 36ths. That's a 36, okay? And so that's the limit. So notice I just direct substitute. Okay, what about here? Well, if I put a -5 in, the squared, I get 25. But if I put a -5 here, I get a -25, so that's 0. So that's not going to fly. So what are we going to do? Well, again, we're going to try to find some function that's exactly equal to this, except at -5. That's what we're going to try to do, and use our favorite property. Well, notice on the bottom I can factor out an x, so that's x plus 5. Okay. What about on the top? Well, let's see. We can factor by grouping. Look, I could take out an x squared and get x plus 5 here. I could take out a 2 from those two, and that gives me an x plus 5 there. And guess what? They have a common factor of x plus 5. So that's equal to x plus 5 times, well, when I divide x plus 5 into this, it cancels and I get x squared. When I divide x plus 5 into this, it cancels and I get plus 2. So what did I just learn? I learned that the argument can be rewritten. This argument can be rewritten, and in the bottom is x times x plus 5. And in the top it's x plus 5 times x squared plus 2. Well, guess what that allows me to do? That allows me to reduce the common factor. And so now I have a new function in here. It's x squared plus 2 over x. And it's equivalent to this function everywhere but at -5. Well, our favorite property says that if two functions are equivalent everywhere but at the x value we're going to, well, then you can just evaluate this limit in place of that limit. They're the same limit. So I put in my -5 and square it, and I get 25 plus 2 is 27. -5 squared is 25 plus 2 is 27 over -5. So, you know, whatever that is. Yeah. What is that? 5 2/5 negative? Okay. What do I do here? Well, polynomials are always continuous. Just direct substitute. Just direct substitute. It's easy because it's continuous. No problems here. When you square root, you get 2. We learned today this is tricky if you're, but for a positive number, that's really easy. It's not tricky at all, and so I get -1. And so this limit is equal to -1. Very good. Okay, we're just following along here. This stuff's easy. It's easy. Why y'all having trouble with this? Okay, because, there's a lot to learn. That's why. Okay? And when I was your age, man, I wasn't even dreaming of doing calculus yet. So what can I do here? If I put the 9 in, it's not going to work for me. Square root of 9 is 3, 3 minus 3, so it's not continuous, so I can't direct substitute. Oh, let's try that little conjugate trick, where you multiply the top by the conjugate of the bottom, maybe, or the top. You just look where you think you need it. And multiply the bottom by its conjugate. So I multiplied by a very fancy form of 1. See, this is 1, okay? And I call this a conjugal visit. Now, I'm not going to actually multiply anything in the top. In fact, I think I factor. Why don't we factor that? That looks like it's something that could factor. So I'm not going to FOIL that out. That's terrible, okay? Because why? I'm hoping that, I get something down here that reduces. And in fact, when you multiply conjugates, you get that squared minus that squared. So what's that going to be? Oh, that's going to be x minus 9. Say, it would be nice if we had an x minus 9 up here. I don't see one. Oh, but there's a 9 there. So maybe there's a 9 there. Let's see. Let's check it. I'd have to have a 1 here. No, I'd have to have a plus 1 here, right? Let's see if this works. So that's a 1, and a -9 makes a -8. And a -9 times 1 is a negative. Oh, it works. Oh, isn't that great? So this is going to reduce with this bottom because the bottom is secretly x minus 9. You maybe should show more work, but I don't have that much time and space. So I'm just going to let that fly. Y'all should probably show more work. And so what do I have? I have this. And I'm going to say that the limit of this is equal to the limit of that by what? Our favorite property, because this function is equal to that function everywhere but at 9. Now, how do I evaluate the limit now? Well, it's continuous. It's it's not a quadratic because the radical, but it's a continuous function for positive x values. So I just put in 9. I get 9 plus 1 times the square root of 9 plus 3. Well, that's 10. And that's 3 plus 3, because this, square root of 9 is 3. 3 plus 3 is 6. And so the limit is 60. And I think that's all the examples I have. Yeah, that's it. So there you go. Math made simple. It's Simpson Math.